Welcome to Maths with EJD. In this video, I'll be considering transportation problem with linear programming. Okay, the transportation problem, there's a group of problems referred to as transportation problem, right? So the transportation problem is a type of optimization problem that deals with determining the most efficient way to transport goods from multiple suppliers, or what you can call sources, multiple suppliers as sources, to multiple consumers or destinations, while minimizing transportation costs. So, I mean, this looks so much like the previous video where we talked about supply chain. So, while minimizing transportation costs. So, the goal is to figure out the goal is to figure out the amount of goods to transport from each supplier to each consumer, ensuring that all demands are met and the supply constraints are satisfied, while also minimizing the total cost. The problem is typically represented in a matrix format where the rows represent the suppliers, the columns represent represent the consumers, and the values in the matrix represent the transportation costs between the corresponding supplier, between the corresponding supplier and consumer. All right. So can we look at the of course the objective of the problem, right? Um, the transportation costs. Okay, I think we've implied that already. Um, Ensuring that all demands are not met. Okay. Yeah, I think it bears repeating that the transportation cost, I mean, the problem, the problem seeks to minimize, seeks to minimize the total transportation cost, the total transportation cost. Yeah, the problem seeks to minimize the total transportation cost. So let's look at the steps required here. Steps, steps to solve, steps to solve transportation problem. Okay, step one would be that you formulate the problem, right? Formulate the transportation table, formulate the transportation table. So here, you organize the supply, demand, and costs in a matrix. First thing. Then number two, you need to find an initial feasible solution. Find an initial, find an initial feasible solution. Okay, here we need to use common methods. So include common methods include the northwest corner rule, the northwest corner rule, least cost method, least cost method, or Vogel's approximation method. Okay. Now, I'm going to take time to treat each of the methods. I'll make a video for each one. So watch out. From this next video, for instance, I'll be talking about Northwest corner rule and so on. So watch out for that. But in this particular video, I'm just going to solve it like the normal linear programming problem we've been solving to get the optimal solution. And then we compare what we will get now, which we know for sure is optimal with what each of those methods will be giving us as we go. So that's the second step. Find an initial feasible solution using um any of the methods outlined. Then step three will be to, after getting your initial optimal solution, you have to now optimize the solution. Or after getting your initial solution, the solution may be optimal and it may not be actually. And then as a result of that, you want to check to see if it is optimal or not. So you optimize the solution, and here you use methods like Modi method, methods like Modi method. Modi method is actually known as, okay, let me just put it this way. Use Modi. Modi is actually modified distribution, modified distribution, modified distribution method. So Modi method. Okay. Or there's also what you can call the stepping stone method. Stepping stone method. So these are two methods. After you've got your initial solution using any of the three methods I've outlined, you can use Modi or stepping stone method to now optimize to check if the solution is optimal. And if it is not, then you optimize or stepping stone method to find um the optimal transportation plan. The optimal transportation plan. Okay. And step 4, right, is to check for optimality. Check for optimality. And how do you check for optimality? You ensure that the current solution, ensure that the current solution is optimal by comparing the total transportation costs. By comparing the total transportation costs. Okay. So you want to see the initial transportation cost you got with whatever you are getting from the optimization you are doing with Modi or stepping stone method. So if what you get after doing that is if the total cost you get is less than the previous one, then it means this is a better solution. Okay, so let's look at a problem. Um, let's look at an example. So suppose three, or rather, suppose there are three suppliers and three consumers, as shown below. Okay, so we now have the table. I mean, you can also refer to it as a kind of matrix. So where you have three suppliers and three consumers. So let me just say this is supplier one, and then you have supplier two and supplier three that way. And you also have consumer one, consumer two, and consumer three. Okay. So that so supplier one, okay, here on this side now. Okay, I guess I need to extend this a little bit more. So imagine that this is the demand side now. Demand, and this is supply. Okay. Supplier one can supply up to 100 units. Supplier two can supply 150, and supplier three can supply 120. Okay. And on the demand side, now, we have uh consumer one requires eight items, 8 units. Consumer two requires 140, and consumer three requires 150. Now, one common thing you may want to pay attention to here is the fact that the most of the times the supply may not be the same as the demand, but to simplify things, right, you need the total supply to be equal to the total demand. So total demand here is like this is 140, 290 plus 80, that's 370. Okay. So here now we have the same 370. So when it is balanced like that, it makes things pretty easy. So you don't have to stress yourself over to do some extra things, right? So, but of course, we also need to know the cost. So the cost to transform one unit from supplier one to consumer one is 8 here. Consumer one to consumer two, supplier one to consumer two, $6. Consumer one, supplier one to consumer three is 10. And we also have the rest like a 9, 7, 4, 3, 4, 2, like this. So that is the table we have right there. And from that table now, of course, so we have that the costs, the costs represent, the costs represent the transportation, the transportation cost per unit of goods. Okay. The supply indicates how much each supplier can provide. How much each supplier can provide. And of course, we have the demand. The demand represents how much each consumer needs. Okay. All right. Then we already know the aim is to do everything in such a way that cost is really minimized. So I'm just going to go ahead and formulate the problem and use Python to solve it in this case. Then in subsequent videos, we now use northwest corner rule, least cost method, and Vogel's approximation in separate videos to see if how the answers compare with what we get here. Now, what we are going to get here using Python is going to be like optimal solution directly. So it's all good to start from here so we can compare results. So we can now talk about the LP formulation here. LP formulation. So first of all, we have the objective, the objective function, just the objective if you like. The objective is to minimize. So we want to minimize Z equals. Now, of course, just like we did for the supply chain thing, here, this variable is like X11. So you can just say supplier one, consumer one, 1, 1, supplier one, consumer two, 1, 2, supplier one, consumer three, 1, 3. So X13. So we have X21, X22, X23, then X31, X32, X33, like that. So it means that the objective function is just simply going to be 8x11, 6x12, 10x13, and so on and so forth. So let's do that. So we want to minimize z, which is equal to 8x11 plus 6x12 plus 10x13, then plus 9x21 plus 7x22 plus 3x31. I mean, just from the table like that, 3x31. I think I've skipped something. So we should have 4x23 plus 3x31 plus 4x32 plus 2x33. That's our objective function, right? So that's the objective function. So the next thing is we can talk about the supply constraints. Supply constraints. So for the supply constraints now, we can look across the rows to see the supply constraint. So supplier one can supply maximum of 100. So it means that if we add up the supply to consumer one, supply to consumer two, and supply to consumer three, everything should be less than or equal to 100. So that is the first supplier constraint. So that is x11 plus x12 plus x13 is less than or equal to 100. And then if you look at the second row, so x21 plus x22 plus x23 should be less than or equal to 150. Okay, so we have x21 plus x22 plus x23 is less than or equal to 150. Then in the third row also, x31 plus x32 plus x33 should be less than or equal to 120. So we have x31 plus x32 plus x33 is less than or equal to 120. So that's about the supply constraints. Then we can also talk about the demand constraints. Demand constraints. So the supply constraint is across the rows, right? But the demand constraint will be down the columns, down the columns. So here now it means that x11 plus x21 plus x31 will be equal to 80. This is what is the consumer requires. So the demands on the demand side, like it is equality, right? On the supply side, it is inequality, less than or equal to. So x11, x21, x31 is 80. So x11 plus x21 plus x31 is equal to 80. That's for the first consumer. Okay. Okay, I did not put this. So this should be like first supplier, supplier one, supplier two, and supplier three. Okay. Yeah, up there then. For the consumers now, I'll come back to talk about that. This is like for consumer. This is for consumer one. So next we have, again, down the column, x12 plus x22 plus x32 is equal to 140. Okay, so we have x12 plus x22 plus x32 is equal to 140. That is for consumer 2. And then we have, lastly, x13. That's the third column now. So x13 plus x23 plus x33 is equal to 150. So that's x13 plus x23 plus x33 is equal to 150 for consumer 3. Okay. So okay, we have non-negativity constraints normally, right? So let's talk about non-negativity constraints. Non-negativity constraints. Okay, so that will be all the xij's greater than or equal to 0 for all I, j. So in essence, that's simply saying that x11, x12, x13, x21, x22, 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 right? x22, x23, x31, x32, x33, all are greater than or equal to 0. That's what that simply implies. Okay, so now the problem has been formulated and we can solve it using simplex method. But as you can imagine already, it's going to be very seriously, it's going to be a tedious process. So what I'm just going to do is I'll just go straight and use Python to solve this. And in subsequent videos, I'll use all these other methods that are well known to be used for transportation problems. So let's go and check out the Python solution to this. Then I'll just come back and talk about those solutions. So here now, we have, of course, we have all the coefficients, right? Especially for the objective function, you have all the coefficients for the matrix. As you can remember from the table, you have the objective function to be 8x11, 6x12, 10x213, and so on, and 9, and so on and so forth. So you have your information here for the objective function. Then for the supply side, you remember you have 100, 150, 120, And the demand side, you have 80, 140, 150. So then you can now do all the variables. Number of supplies will always be the length of the supply. Number of consumers will be length of demand. And, we just put all of that together and we can compute this. So here we find that x x11 is 0, x21 is x21 is 100, x3 x sorry x12 is 100, x13 is also 0, x21 is 0, x22 is 0, x23 is 150, then x31 is 80, x32 is 40, and x33 is 0. Okay, so x11 0, x12 100, x13 0, x21 0, x22 0, x23 150, x31 80, x32 40, x33 0. Okay, so that's what we have from there. So, I mean, for LinProg also, you follow the usual steps and then sorry, we used PuLP first, right? Then now it's LinProg. So the usual way we go and then we just and we get exactly the same results. And the minimum transportation cost, Z, is actually 1,600 in this case. So since we used two different methods and we got it, so we can be sure that for that problem formulated, right, the minimum cost is 1,600. So by the time we use northwest corner rule, least cost method, and Vogel's approximation method, we would see we would always compare with this because I'm going to solve exactly the same problem using those methods. So we can now compare how those methods perform with, the absolutely optimal solution, so to speak. So now that we have our solutions, right, we want to go back and conclude the issue. So we can say, okay, guess I'll change using PuLP or scipy.optimize.linprog in Python. We have the following. First, x11 will be 0. So that simply means that from supplier 1 to consumer 1, okay, no product, no need to supply any product based on the plan. Then we have x12 to be 100. So that means that from supplier 1 to consumer 2, 100 products, right? Supply 100 products. Then x13 is equal to 0. That means from supplier 1 to consumer 3, no products, no products. Then we also have x21. X21 is also 0. That means that from supplier 1 to consumer 1, from supplier 2 rather, from supplier 2 to consumer 1, no products, don't supply any product. Okay. Then from x22 is equal to 0 also. That means that from supplier 2 to consumer 2, no product also, don't supply anything, no product. Then x23 is equal to 150. So it means that from supplier 2 to consumer 3, supply 150 products. Okay. Then we have the last set of variables. So x31 is equal to 80. So that simply means that from supplier 3 to consumer 1, you can supply 80 products. Okay. Then x32 is equal to 40. That means that from supplier 3 to consumer 2, supply 40 products. Supply 40 products. Then x33 lastly is equal to 0. That means that from supplier 3 to consumer 3, no product. Okay. By doing this, okay, by doing this, the transportation costs, transportation costs would be $1,600. Of course, you already know how we get this. So each of these values now you substitute into the objective function. You substitute each of those values here and you get your results. Okay. Um, so and you're going to get $1,600. And since we used Python for this, you can be sure that's the optimal solution. So we can conclude that this gives the optimal solution to the transportation problem. So you have to watch out for how Northwest Corner rule, least cost method, and Boger's approximation method compare with this particular optimal solution. All right. So if you have not subscribed to this channel, be sure to do that right away. Also, hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know if you need to teach a topic or solve a problem. I can find time for that along the line. Then don't forget to like and share so that more people can have access to this great learning. Till I come your way again, keep optimizing. Bye.